Hey, AP Psychology, Mr. Gallagher back at you for another, hopefully 10 minutes or left, little mini lesson in AP Psychology. We move on to Unit 3, Sensation and Perception. Another big one, 11 and 12% of the AP exam will be on this unit. So again, 11 to 12 possible multiple choice questions on the 100 multiple choice question AP multiple choice section, and obviously on the FRQs as well. So I'm going to break this up again into mini lessons. We're going to start with sensation. It's such a cool thing we take for granted. I see stuff, I hear stuff, I smell stuff, I taste stuff, and I feel stuff. And we get this all coming at us at a bombardment, just bombing our senses, everything. Sometimes we get sensory overload, a little bit how it works, and some of the theories behind it. So here we go. Unit 3A, Part 1. All right, after image, I can't do this. It takes a long time, but this is really cool if you get a chance. Stare at this sucker for a minute, then look at a blank white wall and blink your eyes. You'll see an after image. Very cool stuff. All right, sensation and perception. Sensation is how our sense receptors and nervous system receive and represent all this energy. Everything you in your senses involves energy, kinetic, auditory, wavelengths, things like that. Everything is energy coming into us. And it's how our body makes sense of it, okay? Sensation. Perception is how we organize and interpret that sensory information. It gives it meaning, okay? All right, oh, you know this one too. Check this out if you get a chance. There's some vision stuff going on with this, whether you see white, gold, blue, black, so on and so forth. It was quite the rave a couple years back. All right, again, Yanni and Laurel, it's an auditory kind of a test. And again, it's sensation. It's differences we all have, what you hear. Check that out if you get a chance. Okay, in sensation and perception, we have stuff called bottom-up processing and top-down processing. Think of it this way. Bottom up, your feet are on the ground. Your feet aren't very smart. They're pretty dumb. It just, you bang your feet on the ground, it's basic. Bottom-up processing begins with your sense receptors, and it goes up to the brain's integration of sensory information. It begins with the senses, touch, smell, sight, hearing, taste, and it goes up to the brain's integration of that sensory information. Very basic, primal. Top down, top, your head's smart, hopefully. Top-down processing, information processing is guided by higher level mental processes. It is our perception and how we experience and expect sensory information. And it's different for all of us. Bottom out, up versus top down. All right, prosopagnosia is an affliction where some people have sensation without perception. That's right. They can look at their child's face and they don't know who the heck they are. They see the face, they don't know who they are. They have sensation without perception. Dr. Oliver Sacks had this. And this lady here, she tells us a little bit about it. Check it out if you get a chance. Psychophysics, basic principles of how the relationship between our physical characteristics of stimuli and our psychological experience of them. All right, so light, brightness, sound, volume, pressure, weight. That's all it is, weight. Taste, sweetness. It's that relationship between our physical characteristics of stimuli and our experience of that stimuli. All right, I'll check this out. I can never get her to spin around. Every now and then it works. Look at her and you focus for a while and she's spinning one way and then next thing you know, she's spinning the other way. I can't get it to work. It works one time and then I'm done. It's stuck that way. All right, so check it out. You'll see your reverse images. All right, absolute threshold in sensation. Important definition. It's always on the AP test. It is the minimum stimulation needed to detect a particular stimulus 50% of the time. So half the time. It's the minimum to detect it. Sound, sight, smell, taste, touch. All right. You can't, basically the threshold is seeing something. This is examples of it. All right. Now I'm going to give you a better example. If you're in a dark room and you had the ability to dim the light on your phone to an amount so you couldn't see it anymore, that light would still be on your phone, but because of your distance and being in a dark room, you might not be able to see that light because the absolute threshold has not been met. Same thing if you're in an empty room with some sound and you turn the volume up to half of 1%, you may not be able to hear it. It's going, you can't hear it because the absolute threshold has not been met. Make sense? Good. Joey can hear it. Love friends. All right. The JND, just noticeable difference or difference threshold. It's how much a stimulus must change before it becomes different. So I'm talking to you at this level, and I can raise the volume up a little bit more, and you really can't tell until I actually talk down to a level that's noticeably different. And if I just keep talking this level and I keep talking louder, that change. When can you notice the change? That is JND, difference threshold. How much it must change. Weber studied this. Weber's law says to perceive as different, two stimuli must differ by a constant minimum percentage. In light, believe it or not, it has to be at least 8%. So theoretically, I'll give an example here. 100-watt light bulb is on. You're looking at it. That you wouldn't be able to tell the difference in brightness unless that light bulb was 90 or 110-watt bulb. 93-watt bulb, 107-watt bulb, it would look the same brightness to you. Make sense to you? This is, to see difference, it has to vary by this much. That's Weber's law. Sensory adaptation, diminished sensitivity as a consequence of constant stimulation. Go into your room at night, turn all the lights off, and walk in there. It's pitch black. You can't see crap. You're like, oh, sorry. You can't see stuff. You're sitting there going, and it's pitch black, dark. It's dark. And then all of a sudden, you start to see stuff. Your senses adapt. All right, signal detection theory predicts how and when we detect the presence of a faint stimulus amid background stimulation. This depends on a person's experience, expectations, motivation, level of fatigue, etc. So if you are in the woods, all right, and you're walking in the woods and you hear a signal in the background, your detection level of that signal depends on your experience, expectations, motivation, and level of fatigue. If you're tired, you're probably not going to notice it, or maybe you'll notice it more. It just depends on how your body reacts to it. Okay? How do I get back here? All right. I can go to the next slide. Hold on. I'm in a bit of a precarious situation here. How do I get rid of this pen here? Oh, here we go. All right. Transduction, very important. Transduction is the conversion of one energy form into another. Like I say, when you see stuff, it's light coming in your eyes. That light energy has to be converted into another form of energy to give us meaning in our brain. So in vision, transduction happens in the retina, okay, in the retina. In sensation, transformation of stimulus energies into neural messages. We change it from sound waves, light waves, energy into a neural message that our brain can understand. In vision and in sound, actually, we have wavelengths. The distance from one peak to the next measured in nanometers. A short versus long wavelength determines the color you see, from blue to red, or the pitch you sound from high to low. The intensity is how tall those peaks are. High peaks versus low peaks. Bright colors have high peaks. Pastel or dull colors have low peaks. Loud sound has high peaks. Soft sound has low peaks. Take a look at this. This will give you an example of what I'm just talking about in that prior slide. Again, trying to keep 10 minutes left, so I'm rolling through this stuff. All right, in your eye, major parts. Check them out, learn them, understand them. Pupil, black thing, adjust, and lets light into your eye. Iris, that is your color of your eye, brown, blue, green, whatever it is. It's a muscle of color that controls the size of the pupil. And the lens is behind the pupil, and it focuses images to the back of your eyeball, the retina. Accommodation, the process by which the eye's lens changes shape to help focus near or far objects on the retina. That's on the back of your eye. It focuses it. The lens does. The retina is very important. This is where transduction takes place in vision. It changes light energy to a neural message to go to your brain, your occipital lobe, so you can understand it. Very light sensitive. It has rods and cones and layers of neurons that let us see. All right. Good picture here for reference. Check it out if you get a chance. Acuity, how sharp your vision is. All right. On your TV, you go to sharpness. It makes it either dull or very detailed. Okay. Nearsighted. Nearsighted people who have vision problems can see close, but they can't see far. Farsighted people with vision problems can see far, but they can't see close. These are readers. My far vision is fine. I can see far. It's no problem. But as you age, your lenses change. I noticed about 5-10 years ago, I had trouble reading fine print. I had to get reader glasses. So now because my lens not focusing on the near stuff, it can see the far stuff, but the near stuff, it struggles. So I'm farsighted. Here's an example of what I'm talking about there. All right, rods and cones. Summarize this for you guys in a couple seconds. Rods detect black, gray, and white, twilight or low light. They help you see in the dark. We don't have a lot compared to other animals. All right, cones, see, however it looks to you guys, see, for color, is near the center retina. They deal with colors, and they're really good in daylight or well-lit conditions. At night, our cones don't do much. Our rods keep us going, and that's why as it gets dark, colors fade. All right, optic nerve carries that transduced message from the retina to the brain, the occipital lobe. Blind spot and fovea, more important information that cluster around the retina. 3 types of cells in the eyes: horizontal, amacrine, and ganglion. All have their own function. I gave you that at the beginning. I showed you that, what do you call it? The after image of the flag. That they give that credit to horizontal cells. Okay, so again, the eye anatomy is pretty detailed, so take your time and learn that well. All right, feature detectors are in your occipital lobe, back here. They include simple cells, complex cells, hypercomplex cells. They help us see lines, edges, motion, color, and complex shapes. They make sense of that information being transduced from the retina through the optic nerve to the occipital lobe. Okay, again, rods and cones. Parallel processing, almost done here at this little section. Instead of step-by-step processing, our brains process several things at once. Color, motion, form, depth. If you're a baseball player, you're sitting there, you see the pitch coming, you can judge the distance, the speed, the spin, the color, and the shape all at one time. Our eyes are pretty awesome. Trichromatic theory of color, 3 different retina shapes, and I'm going to actually wrap up this mini lesson right now before I get going any further. So, Unit 3A, Sensation, Part 1. I'm out.